So this is a simple methane reformer model. If you look here in the middle of the model, what you see is an equilibrium reactor, what we're using for methane reformation. It basically has two inputs. The first input we refer to as the heating flow. It's basically a mass flow going into the reformer to provide heat for the reaction to take place. The second flow, referred to as the reactive flow, is the mixture where the actual components and their actions are going to take place. So in this case, we have a mixture of methane and water that are forming the reactive flow, and the heating flow is heated using a lambda burner. So how do I define my chemical reactions? How do I specify what my equilibrium reactor is like? To do this, I will go through into the mask of the equilibrium reactor, or the methane reformer in this case. As you can see here, you can define the chemical reactions by giving in the equations simply as you would write them. In this case, we specify two reactions for methane reformation. Also, we can specify here, like the thermal mass of the methane reformer, how much heat exchange takes place between the flows, how much heat exchange takes place between the reformer itself and the environment, and many other properties. Once I click OK and run the model, the block will take care of calculating and simulating the chemical reactions taking place inside of it. Going back to the model, you can see here, using the flow displays I have attached to the second flow, what we have is an incoming flow of 25% methane, 75% water. At the output of the flow, the temperature increased significantly, and most of the methane is gone. Now we have the resulting elements like carbon monoxide, carbon dioxide, and hydrogen gas. What's also important in thermodynamic modeling, and a very important feature, is thermodynamic balancing. What that means, we have to ensure that our system is balanced and consistent with the laws of thermodynamics. That is, the net mass of elements is zero. No mass appeared or disappeared during the simulation. So how do we do this? Our solution was, during the simulation for a defined period of time, we collect information about all the mass flows going in and out of the blocks. At the end of the simulation, using a simple command line, we gather this information, calculate it, and export the results to an Excel sheet so that we can see that the net result of all the incoming and outgoing masses was zero. So the resulting sheet looks something like this. Please forget about all the details. It's too complicated to explain now. The idea is that listing all the blocks, you can see here on the top part that the hydrogen, carbon, oxygen, and nitrogen, the basic elements in our models, their net balance was zero, which is what we used to ensure that nothing appeared or disappeared in the simulation. These results can also be exported to text files. Going back to the concept I introduced earlier about downloading data from chemical media databases, what I wanted to show you here is what such a database would look like. So the database is usually, but not necessarily, defined in an Excel sheet, and each element, many different properties are listed there. And if you just want an extra element, you just define it here in this database. Using a provided tool, you export it into a mat file and load your mat file here. Then you'll be able to see your new compound in this list and select it in the model, just like I explained earlier. Finally, we'll move to the architecture part of the library. So how do we build a tool for modeling thermodynamics? At the core of the library, we build a basic level of fundamental blocks that calculate fundamental thermodynamic properties, according to the principles of engineering thermodynamics. These cover stuff like state changes and state equations, compressions, expansion, condensation, vaporization, and so on, basic thermodynamic behavior. These blocks are then used to build actual Thermolib components, that is, real-world components like pumps and valves and chemical reactors and fuel cells and so on. The beauty of such a design is that you can use the basic blocks to build user-defined component. That is, the user does not have to re-implement the thermodynamic equations to make a new component in the library. And it's frequently the case that users need to define their own specific components for their system. The basic level is built using C code. But the Thermolib components are built using Simulink code, and this is done on purpose. Why? Because the basic calculations, there is no need to change them in a regular implementation. But the components, the user might need to change the implementation to fit their particular need. And this is why the code there is open in Simulink, so that changes are possible. Also using this basic code is the command line functions. That is the same functions that you can implement in Simulink. You can also implement using the Matlab command line. This was also done on purpose so that a lot of scripts are done in Matlab and not in Simulink, and we have to have the ability to use these basic thermodynamic calculations in these scripts. So we have one final small example to demonstrate these basic blocks and the command line function. So the example we have is of isobaric evaporation, that is evaporation happening at the same pressure. Please forget about all the details here and focus on this one small block TP state. This is a basic block. What it does is you give it some information about the mass flow that's going in it. In this case, we only give it the temperature, pressure, and the mass flow. And then it calculates the rest of the properties of the flow bus, like the vapor fractions, entropy, enthalpy, specific heat, and concentrations. So what we did here is, for a certain flow, we varied the temperature, and then we looked at how does the entropy vary itself with this. And the result is the so-called TS diagram. We've simulated this at different pressures, and I'm sure many of you are familiar with this basic thermodynamic diagram. This same example we just saw here as a Simulink model, we can repeat it in Matlab code. So what we have here is the same function, TP state. We give it the temperature, the pressure, and the component, and it calculates for us the rest of the properties like the enthalpy, entropy, and so on. And using this one command line, we can reproduce the result we just reproduced in Simulink, this TS diagram. So we've almost reached the end of our presentation. I'll wrap it up with a summary of the key features of thermodynamic modeling. It has to be based on fundamental thermodynamic principles, and it should handle various functionalities like what we showed you today, in addition to others like hydraulics and pressure feedback. We've also tried to show you how a well thought out tool can be used to model thermodynamics in a wide array of applications with focus on thermodynamic systems. What kind of applications? Well, we've used these basic tools to model applications in thermodynamic processes, cooling, heating circuits, thermal power plants, heat pumps, fuel cells, heat engines, and many others. This was my presentation for you today. Thank you for your attention.